Close the door back here. Dear Father, we thank you for this day. Again, I thank you for this class. Just ask you to bless our work today. Help us to glorify what we do and just understand a little bit more about your creation together, Lord. In my prayer, Lord Jesus. Amen. So today, I want to tell you guys about boundary value problems. And hopefully, maybe a little bit about Fourier series. All right. So, first of all, what on earth is a boundary value problem, right? So, generically speaking, a boundary value problem is one which involves a differential equation where you have data about the solution at not just one, maybe one time, but two times. So the problems that we've solved in here have all been initial value problems. Initial value problems, we have a differential equation and we have a bunch of data at one particular time, right? We specify like the position, the velocity, at one particular time, and it turns out that if you're given a position and a velocity at one particular time, then there's a unique solution, right? And we've found them, a lot of them. Boundary value problems are a little bit different. So it turns out that the boundary value problem may or may not even have a solution. So let's look at a particular example. So here's a problem. And we have to be a little bit cagey about it because we're going to consider not just one differential equation, but actually a whole family of them. So we're going to determine which values of k, all right, allow solutions of y prime prime plus ky equals to 0, all right, subject y of 0 equals to y of L. All right. So this right here, my friends, these are the boundary conditions. Or if you like, BCs. All right. And here, by y prime prime, I mean the second derivative with respect to x. All right. So we desire a solution for 0 less than or equal to x less than or equal to L. And to be clear, y prime is a notation for dy dx, etc. All right? This marker's dead. Aw, man. No buckets. No buckets. Anyway, so how do we solve this problem? What do we do? We need to break into cases. What are the cases? Nah. Oh well. This k, right? It could be different things. And depending on what k is, we have very different looking solutions, right? Like if k is 0, then what are we looking at? Let's start with that. What's k equal to 0 going to give us? K equals to 0. We're looking at y prime prime equal to 0, right? The solution is y of x equals to ax plus b. Yeah? And if we apply the boundary conditions, what happens? We get y of 0 is b, and y of L is equal to AL plus B. And I think I'm forgetting something. Yeah, I don't just want these are equal. I want these are both fixed to be 0. All right, that's what I want there. Sorry, my notes. I'm a victim of my own notes. We're in chapter 8, by the way. But anyway, so I want this equal to 0 and this equal to 0. Lo and behold, A equals to B equals to 0. So nothing. Interesting. Here. Right? Because the only solution we find is the 0 solution, and we're looking for non-zero solutions, all right? Of course, 0 solves this, yeah? The constant function 0 solves it, great. What's the next case? Case number 2. How about k less than 0, right? Then we can write k is equal to, and I'm going to do something a little bit weird here, all right? So watch me. Minus beta squared, where beta is positive. I claim there's no loss of generality there, right? If you have a negative number, certainly we can write it as minus the square of a positive number. Now, why would I do that? The reason I would do that is then when I look at y prime prime plus ky, I have y prime prime minus beta squared y equals to 0, right? And I know how to solve that, right? I know how to solve that. The solution to that has the following form. It looks like y is equal to a cosh beta x plus b sinh beta x, yeah? That right there is that's the solution. Coshes and sinh. You're like, no, it should be e to the beta x and e to the minus beta x. We don't disagree. I just prefer to write it in terms of cosh and sinh. Right? If you don't like this, aka c1 e to the beta x plus c2 e to the minus beta x. You can rewrite this. You can rewrite that in terms of cosh and sinh, but trust me, cosh and sinh are the way to go here. It makes the analysis of the boundary value problem way, way simpler. Okay, so that's my general solution in this context. Are there any actual solutions to find, though? See, because we have to satisfy the boundary conditions. What do those mean here? Apply the boundary conditions. We have y of 0 is a, and y of L is equal to, well, a cosh of beta L and plus b sinh beta L. Now the reason I know that y of 0 is just a is because sinh of 0 is 0 and cosh of 0 is 1, which is why I used cosh and sinh here. So we have a is equal to 0 from the first one, which then tells me that, in fact, b times the sinh of beta L is equal to 0. Now sinh is an increasing function everywhere because its derivative is cosh, and cosh is greater than or equal to 1. So sinh always increases at a rate of 1 or higher. That means that sinh can't double back on itself. The inverse hyperbolic sign is defined. We can take inverse hyperbolic sign of that equation, and it gives us that basically b, getting to the point, this only allows b equal to 0 as a solution, all right? This implies b is equal to 0 because sinh of beta L is non-zero, okay? Well, this is very boring. Again, nothing. So, nothing to see here, right? Nothing to see here, case 2. I sure hope we find something in case 3. What's case 3? Yeah, 3 is k greater than 0. So we are going to put k equal to beta squared for some positive beta, right? And then what are we solving? We're solving y prime prime plus ky, which is in this case y prime prime plus beta squared y is equal to 0. What is the solution to that differential equation? So the solution to this is simply y is a cosine beta x plus b sine beta x, right? If you like, we could write down the characteristic equation. The characteristic equation's lambda squared plus beta squared, lambda squared plus beta squared equal to 0, which has solutions beta equal to lambda equals to plus or minus I beta, right? And so that's why we get this, yeah? So this is my general solution, yeah? We have not yet applied the boundary conditions, right? So apply the boundary conditions. What happens? We have y of 0 is a, and y of L, which is, by the way, 0. And so y of L is just equal to b times the sine of beta L. And that's supposed to be equal to 0, right? It's starting to look like everything's going to be 0 again. This is so embarrassing. Why did we even have this discussion? There's no solutions to find except for the 0 solution. Wait a second, though. This is sine. When is sine 0? Well, like the inverse sine of 0 is 0, right? So it's only 0 for 0? Wrong. Sine is 0 for what? If I have sine of theta equals to 0, what are the solutions to this? This is true if and only if theta is an element of pi z. In other words, if and only if theta is equal to n pi for n an integer, right? Any integer multiple of pi gives us that sine of that multiple of pi. It is 0. Aha! Well, now we've got something. So if we put beta L equal to n pi, right, for n and z, we can solve for beta, right? Beta is equal to what, apparently? N pi over L, right? Now, to be clear, can we allow n equal to 0? Think about this. N equals 0 is not allowed because we assume beta is positive, right? So that's an extraneous solution, right? It's not even in the solution set. Did I ever, guys, tell you that if I was a rapper, I would be called extraneous G, and my tagline would be, I'm not even in the solution set? It's true. I say this. Drop the... Yeah, that's all I got. But yeah, so n can't be 0, and without loss of generality, we might as well suppose that n is positive. If I put n as negative, it's the same solution, right? Because we'd just be flipping like n to minus n in the cosine and sine. That's not a different solution. That's linearly dependent. So we can just, without loss of generality, suppose that n is a natural number. Aha! Finally, we found a solution. So that's it. But take a moment to appreciate how perverse this is. I'm saying that this kind of differential equation can only have a solution if it's a particular kind of this differential equation, right? I'm putting a constraint on the differential equation itself in order to have a solution. See this? So so for example, if I had, if I wanted y of 0, equals to y of 1 equals to 0 for, y prime prime plus 3y equals to 0, I think I'd be out of luck, right? Because in this case, my k would be equal to 3, and I would need that to be equal to beta squared, which apparently has to be n squared pi squared over L squared, right? Now that would have to be n squared pi squared for our particular context, because this right here tells me that L is equal to 1 in my context, right? There's no way I can choose an integer, n, such that n squared times pi squared is equal to 3. So it's impossible to solve that differential equation subject to those boundary conditions. We just can't do it. Unless what? There's only one way to solve it, and it's a boring way. It's the zero solution, right? Just the zero solution. So, in summary, we have a theorem here, which I call proposition 8.31. Right. And this is, element of the natural numbers. All right, so I'm going to write this result over here. Proposition. I can't spell. Prop 8.3.1. It says that the non-trivial solutions to y prime prime plus ky equals to 0, subject y of 0 equals to y of L equals to 0, have the form y sub n is equal to, like, some multiple, let's say bn, times the sine of n pi x over L for n equals to 1, 2, 3, and so forth. Moreover, solutions exist if and only if k is equal to n squared pi squared over L squared, all right? So if we're up against this problem, y prime prime plus ky equal to 0, subject to the boundary conditions that they have to vanish on the endpoints, the only way we can solve it is if our differential equation has the particular form that the k is equal to n squared pi squared over L squared. And in that case, we just get basically sine functions as solutions. All right? This is really different than what we've done before, right? Because before, I just give you a differential equation, right? I don't give you the freedom to change the form of the differential equation to make it work. But we have to have that freedom here in order to find solutions, So it's really quite a little bit different. Let us look at a slightly different problem that's kind of the same. What if instead of making the endpoints be 0, we make the endpoints motionless? What if we make y prime of 0 and y prime of L equal to 0? How would that go? Notice that, like, the case 1, 2, and 3 will go exactly the same. All right? So let me state the problem. The problem I want to study next find non-trivial solutions to y prime prime, y prime prime plus ky equals to 0, subject boundary conditions y prime of 0 equals to y prime of L equals to 0. All right? We can make the same breakdown of cases, right? So at case number 1, we have k equals to 0. We have y is ax plus b, right? Now y prime is a. So what happens? We get y prime of 0 is equal to a is equal to y prime of L, right? So apparently a is equal to 0, and oh, hey, look it, we get y of x is equal to b. So if you like, we could maybe say y sub 0 equals to b. Behold, a solution from the 0 case. We could just have the constant solution. All right? So there's something. What's case number 2? Case number 2, k less than 0, right? So there we had y is equal to a cosh beta x plus b sinh beta x. We calculate the derivative. Y prime is a beta sinh beta x plus b beta cosh beta x. Sorry about my b's and betas, but my beta's got a tail, so you can see the difference, right? Okay, apply the boundary conditions. We get y prime of 0 is equal to b beta, and y prime of L, which is equal to 0 by assumption, all right? And y prime of L, so that says that b is equal to 0, right? And y prime of L would give us that a beta sinh beta L is equal to 0, so therefore a is equal to 0. Because sinh of beta L is non-zero. Throughout this whole discussion, I'm assuming that L is non-zero, right? If L is equal to 0, that's just dumb, right? And if L is negative, that's also kind of dumb because I went from 0 to L for my domain of the solution, right? So we're assuming L is a positive number. So in summary, for case 2, nothing. So nothing. Nothing to see here, right? Case number 3. All right, case number 3. We have k greater than 0. In other words, k is equal to beta squared. And we've got ourselves a y, a cos beta x plus b sine beta x. That makes y prime minus a beta sine beta x plus b beta cosine beta x by differentiation, right? Apply the boundary conditions. What happens? I'll do it on the up over there. You can see it better. We apply the boundary conditions. Y prime of 0 is, the sine of 0 is 0, so we just get b beta cosine of 0 is 1. So this time b is equal to 0. Y prime of L is what? We've got a minus a beta sine of beta L is equal to 0. Aha! We've run up against this in the previous discussion, right? How can we make this 0? We need beta L equal to n pi for some n in the integers, right? In order to get that to be 0. Lo and behold, we find that we have solution yn equal to, let us say, we could say a sub n cosine of n pi x over L, right? And k, of course, is equal to beta squared, which is n squared pi squared over L squared, right? So that gives us proposition 8.32, which says that if y prime of 0 is equal to y prime of L is equal to 0, then we get yn is equal to an cosine of n pi x over L for n equals to 0, 1, 2, 3. Da, 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 da. See what I did there? I did something a little bit sneaky. I lumped in the 0 case because cosine of 0 is what? 1, right? So I can lump in the constant case into the cosine solution if I want. Yeah? So far, so good? Now, you might be wondering, why on earth are we doing this? There are reasons. All right. What's the next thing we might try past this? How about, what if we have one of the sides position is fixed to 0, but the other side, the velocity is fixed to 0? That's another case we could consider, right? So how about this? We just erase the prime here, like that, and study that problem. How would that be different? Right? So I just erased the prime here. Yeah, you have to rewrite it. That's okay. That's your job. It's not a bad job to have, you know? There's a certain joy to being a student. It's got this, like, certain simplicity, When the semester is done, the job is done, whether you like it or not, right? Well, in principle, it's done. Unless something really bad happens, Regular jobs in real life do not have this, typically don't have this sort of definitiveness, like, oftentimes you're not really sure exactly what your job is. And you're not really sure ever that it's done. This is like a large part of jobs that exist in industries. Like, what exactly are you supposed to be doing? You should be doing something, right? But once an industry gets sufficiently large, this is especially true of the government. It may not entirely. So this thing that Musk did with asking people to send an email with the 5 things they were supposed to do last week, that's actually really terrifying as a government employee because you might not know what you were supposed to be doing last week. That seems like a very silly request. It's actually very much not a silly request at all. Because when I was working for the government for a year, sometimes I really didn't know what I should be doing in a given day. Honestly.
Do they not let you tasks?
No, I had 2 bosses and it wasn't clear who was primary and or what I was supposed to be doing. I don't know. I mean, I did stuff. I did stuff. I learned things. But anyway. I mean, you're supposed to fill out a time card. I spent 10% of my time working for the government filling out a time card. Taking account of when I was working. Very important. You have to check that box. It becomes very clear if you're not doing that, Anyway, I digress. How about this? So, case number 1, k equals to 0, y of x equals to a plus, ax plus b, right? That's the general solution in that case. Y of 0 is equal to b is equal to 0. Y prime of 0 is equal to a is equal to 0. Y prime of L, rather. So apparently, nope, nothing, right? Case number 2, k less than 0, that is to say k is equal to minus beta squared. We have y of x is a cosh beta x plus b sinh beta x. Yeah? So y prime of 0 is a beta sinh beta x. Not 0, I just want to put x here for the moment. Sorry, guys. Sinh beta x plus b a cosh beta x. By the way, think about this. If we had not used cosh and sinh, every time I did a cosh sinh calculation, if you used e to the beta x and e to the minus beta x, would be solving a system of equations in C1 and C2, working through it. They're not bad, it's 2 equations and 2 unknowns, but because we used cosh and sinh, it became easier, much easier. Anyway, so, okay, great. Y of 0 is a, which is 0. Okay, great, know that. Y prime of L is what? B beta cosh of beta L, I think, yeah? Which implies, so cosh of beta L is not equal to 0, so this implies, so this being equal to 0 implies that B is equal to 0. All right, so no solution again. So finally we come to case 3, right? So in summary, nothing. Nothing here. K positive. K positive, what we got? K equals to beta squared, y of x equal to a cosine beta x plus b sine beta x. Y prime of x is minus a beta sine beta x plus b beta cosine beta x. You guys have a question?
Yeah, I do.
What's up?
Why is it, like when you did the y prime of L right there, for the caution, why do you only write, kind of a question, b beta cosh of beta L? Why don't you write the a beta sine sinh?
Oh, because a is 0 from the previous step. So we're solving both of the boundary conditions at once. So once we know it's something 0, then it's dead to us. So, yeah. All right. Now that we have the general solution and its derivative, let's apply the boundary conditions. Y of 0 is 0, but it's also a. Good to know. Y prime of L is b a beta cosine of beta L equal to 0. Now that's interesting. We're going to have to think about this for a second. How can you get cosine of an argument to be 0? Like, what's the solution in general of cosine of theta equals to 0, if and only if what? Pi, if we had cosine of pi, it would be minus 1. Cosine of 2 pi, 1. Pi over 2. Oh, cosine pi over 2. How about minus pi over 2?
Yeah, all of those.
And so any what? Any odd integer multiple of pi over 2. Which is to say anything of the form 2k plus 1 or minus 1, whatever, times pi for k in, if we put a minus here, that's helpful. So we could just say 2k minus 1 for k, an element of the natural numbers. Or I don't know. If you don't like k, you could use n there. The point is that starts at pi. Oh, my bad. It starts at, I need to divide by 2, yeah? Oopsie. So that starts at pi over 2. Then next is 3 pi over 2, and so forth, right? If you put k equal to 1, we get 2 minus 1, which is 1. Put k equals 2, we get 4 minus 1, which is 3. So we get 1, 3, 5, 7. Why don't, and that's enough, right? Because if I put in the minus pi over 2, minus 3 pi over 2, those solutions, I'm not getting anything different as we think about the solutions that we're creating, right? Because we would just be like putting in minus the angle into sine and cosine. That's not a different function. It's the same function. Let's just keep one. One copy is enough. Okay, so there we go. Proposition 8.33. Let me double check on that in terms of my enumeration. Yes, I put y of 0. So, okay, great. So there we get if y of 0 is equal to y prime of L is equal to 0, then my solution has the form, which one survived? The b, right? So sine. So like bn, sine of what? Well, all right, let's be careful here. So we had beta L is equal to 2, I'm using n apparently, so 2n minus 1, sorry guys, times pi over 2. I switched back to n rather than k, that's okay. If it's not, well, sorry. So switching back to n rather than k. So my beta is 2n minus 1 times pi over like 2l, which makes the, all right, so we got 2n minus 1 times pi x over 2l. That's my function, and k, of course, is equal to 2n minus 1 squared, pi squared, divided by 4l squared, I think, yeah. Yes, sir.
Why did we go back to sine in the proposition from the cosine we found of PL or beta?
Yeah. Why did we do that? What's the logic here? So the logic is, this is the general solution, right?
Oh,
Right. No, it's a good question. So that's the general solution. We differentiated it. We applied data, right? And that gave us the equation that a equals to 0. A equals to 0 blanked this piece out, right? And so we're just left with that piece. And then I slapped an n on it to recognize that there's not one solution. There's one for each possible n. Only if this differential equation just so happens to have the right form, right? It has to have the form that the k, defining the differential equation, right, like this, that k must have the form 2n minus 1 squared pi squared over 4l squared. So, like odds are stacked against us to find a solution if we just have a differential equation in the wild of this form, right? It's a pretty special thing to have a solution that fits the boundary conditions.
I looked at the derivative and saw e equals
Yep. Yeah. No, a totally reasonable question. So I think you can guess what's going to happen for the next case would be what? We could have y prime of 0 be 0 and y of L be 0, right? And that's in my notes. I'll let you look at it. I'm tired. This is enough, all right? So why are we doing these? Why are we doing these? The reason we're doing these is that I'd like to show you guys how to solve a number of interesting partial differential equations. And in order to do that, we end up finding ourselves facing these particular boundary condition problems in the midst of the problem. And it's nice to kind of like partition off this part of the analysis and just encapsulate it as some theorems that we can refer to. So, like in the upcoming lectures, when I'm solving a partial differential equation, and we get to a certain boundary value problem, I'm just going to be like, hey, we already know what happens here. It's this, or this, or this, and we'll just write it down. All right? And of course, also, in like quiz 5, I'll just give you some problems which use these results, kind of like my example 1, right? Now, in times past, I didn't have my notes, and when you're coming to a different partial differential equation, you just solve these, go through this analysis in the context of that problem, you know? But I realized over the years, after I kept doing them, that it would be smarter to sort of write down these as theorems that we could use to kind of streamline the calculation a bit. So that's the logic. Now, of course, I probably should show you, like, what do I mean, partial differential equation? Yeah? So the first one to think about is the heat equation. So the heat equation, it models the flow of heat, if you will, on, like, perhaps a rod. It could be a metal rod or something. And we usually use U for the temperature of the rod. So just to draw a picture, the heat equation, and of course there's not, I mean, this is just an example of the heat equation. The heat equation's a more general idea than just the heat on a rod, but that's where we start. So x equals to 0 here, x equals to L here, and then at a particular point on the rod, we can talk about the temperature at that x at that time. So this is the temperature at position x at time t. And it turns out that we can write a partial differential equation which models the change in temperature with respect to position and time. But we're talking about a function of two variables. So there are two independent variables here, namely position and time. And the equation is as follows, I believe. Partial squared u, partial x squared, is equal to, let us say, man, I forget where the constant goes, but I'll put it over here. Alpha times partial u partial t. I mean, you could, something like this, all right? What I'm debating is whether the constant properly belongs here or here. It's not really important. Most of the time I make that constant 1 just to keep things simple, but let's put it there for the sake of the moment. This is a partial differential equation. Now you've solved some of those in this semester, right? Every time you found the potential energy for the conservative vector field, that was a system of partial differential equations you solved. Exact equations, you had to solve partial differential equations, one for m, one for n, right? Partial f, partial x equal to m, partial f, partial y equal to n. Those were partial differential equations. You solved them, you know? So you have done a little bit. But this is a little bit not quite the same as what you've already done. Now, so like this notation is kind of obnoxious. So, you know, sometimes we'll talk about it as what, like uxx equals to alpha ut, all right? Like that. So here's the thing. Fourier, early 19th century mathematician, was interested in solving these kinds of equations, the heat equation. And one of the things he did was to propose that the solution could be written as a product solution. And what that means is that we could write u of xt as equal to some function just of x times some function just of t. This is the product solution. Conjecture, if you will. It turns out to be a pretty good conjecture because it works. And so if you have a product solution, so x is just a function of x, big T is just a function of t, when we take partial derivatives, it's particularly simple. See, ux is just x prime of x times t of t, right? And I'm just going to write that as x prime t if you guys don't mind. And if we calculate uxx, we just get x prime prime t. See, t has no x dependence, so it just differentiates like a constant. It just doesn't differentiate, yeah? How about ut? You guys tell me, what would ut be? I'll write it out. That means partial t of big X times big T. What's that equal to? Yeah, that's X times, you said X times T prime? Great. That would be correct. All right, so put those in. What does this give us? We put them in, we get ourselves a X prime prime T is equal to alpha times xt prime. Now you might say, well, how does that help? How does that help at all, right? I don't know. What do you think? Does it help? Can you solve them separately? But they're not separated, right? So this is why it's called separation of variables, what I'm about to do, because we're going to separate the variables. And the way that's done, watch it, very complicated. We divide by the solution. The x and the t, they be canceling. So we get x prime prime over x equals to alpha t prime over t. Think about it. Think about this equation we just found. Think carefully about it. On the left-hand side, we have just a function of x. On the right-hand side, we have just a function of t. What kind of functions are only functions? What kind of functions are common to both time and space? They're the only kind. The purely constant functions, right? So the only way I can have this ratio equal is if it's equal to a constant. And for reasons of connecting with what else we've done today, I'm going to set that equal to, not k, but minus k. The reason for that is if I do that, then this becomes x prime prime plus kx is equal to 0, and, well, alpha t prime equals to minus kt. Or if you like, alpha t prime plus kt equals to 0, right? ODEs. Ordinary differential equations. One in x and one in t. We know how to solve those, right? The reason I put a minus k there is so it matches my propositions. Yeah, you see that? So, just a sneaky step, but all right, so we're talking about the temperature on a rod, right? One thing you could do would be to put both sides of the rod into ice, right? What's the temperature of ice? Centigrade. 0, right? So if we put an ice bath on both sides, we have like u of 0t is equal to 0, and we have u of, lt is equal to 0. Yeah? But if you think about that, think about this product solution, right? If we have u of 0t, we're talking about x of 0, t of t equal to 0, u of lt, x of l, t of t is equal to 0. These right here are holding for all time. What does that mean? If those hold for all time, well, if the time solution is identically 0, then we just have the 0 solution. That's not interesting, right? So it must be that the time solution is non-zero. So the only way that the solution then could satisfy these boundary conditions is if the spatial part of the solution, the x part, itself satisfies the boundary conditions that we looked at to start with today, right? So this tells me, in fact, x of 0 is equal to 0, and x of l is equal to 0. Aha! So we know what the solution looks like then. in the ice bath case, right? What's the solution look like? So we're up against x prime prime plus kx is equal to 0 with x of 0 equal to x of L equals to 0. Therefore, k must be equal to n squared pi squared over L squared. And we have x of n of x is equal to, man, I've forgotten already, b sub n sine of n pi x over L. Right? So, hey, we already found the spatial solutions. And embarrassingly, not just one solution, right? Infinitely many. So then what? Well, we still need to solve the temporal equation, right? We're still up against, we still got to solve what? Alpha t prime plus k, what was k? N squared pi squared over L squared, yeah? Times t equals to 0. But that's a first order ordinary differential equation. We can solve that easily, right? This gives me the characteristic equation alpha lambda plus n squared pi squared over L squared is equal to 0. Therefore, lambda is simply minus n squared pi squared divided by alpha L squared. And hence, my temporal solution, Tn of t, I can simply write as the exponential of minus n squared pi squared over alpha L squared times time. So this tells me then that I have what's sometimes called an eigensolution, un of xt, is equal to, well, something like bn sine of n pi x over L e to the minus n squared pi squared t divided by alpha L squared. So let's think about this though, right? I tell you you've got a rod, right, that has fixed endpoint temperatures of 0. What else do you need to know in order to make sense of this problem physically? Don't you also need to know what the initial temperature distribution is of the rod? Right? So you need, the boundary conditions are that the endpoints of the rod are fixed at temperature 0, but we also need to know what the temperature is at each point on the rod. So that's the thing that's missing from the problem so far. So we should also consider be given an initial condition, which is to say u of x comma 0 times 0, let's make that the initial condition, equals to like f of x. So this is the, initial temperature distribution. Right? Maybe right before you set the thing free, you got a match and you heat up the middle of the rod super hot, and then what happens? If the ends are an ice bath, then that temperature is going to, it's going to smooth out. Eventually the temperature should be 0, right? Like long term, if you just heat it up before time 0 and then let it go, let it cool off, yeah? Okay, so there's, so we have these solutions, right? And so what's done is you let u of xt equals to the sum n equals 1 to infinity of b sub n sine of n pi x over L e to the minus n squared pi squared t over alpha L squared. So this is the genius of Fourier. Fourier said, I can just take these product solutions I have and I can take an infinite series of them because every single one works. So just keep adding them together and put appropriate constants in the front, b sub n. You're going to select those constants to do what? If we select those constants properly, we can fit the initial condition. All right, so what does that mean to fit the initial condition here? What was Fourier claiming when he says you can fit the initial conditions with this so-called the red box solution I just gave you guys? What does that mean mathematically? Let's look at that. What is that saying? So to fit the initial condition, we need f of x equals to u of what? X comma 0, right? But if I plug that into my handy dandy series, what do I got? Sum n equals 1 to infinity. And we're putting time equals, what happens with time 0 in this solution? E to the 0 is? 1, right? So we just get Bn times the sine of n pi x over L. So you see, Fourier's claim that the solution to this heat equation can be written as an infinite series of these eigensolutions is tantamount to the claim that any initial temperature distribution can be written as an infinite series of sine functions. Now, I think other mathematicians at the turn of the 19th century have been like, that's crazy. You can't just build any function from a sum of sines, right? Can you build any function from a sum of sine functions? Well, the answer is yeah, usually you can. This is called the Fourier decomposition in honor of Fourier. So in order to find the Fourier decomposition, we have to figure out what those b sub n's are. How should we do that? Right? Like, if we had a power series, you guys know what to do, right? Like if I was saying f of x is equal to the sum of like Cn, x to the power n equals 0 to infinity, you guys at this point in your life ought to have an idea how to find the c sub n's, right? Like C0 is f of 0. C1 is f prime of 0. C2 is f prime prime of 0 over 2, right? This is Taylor's theorem. So we're asking the question, what's the analog of Taylor's theorem for a Fourier series? So what we do, it turns out, is multiply this by, I want to say, sine. Let's see here. If we look at, I'm just going to look at this here, if you don't mind. So we're going to take, rats. I'm trying to think of how to write this. I usually have the good sense to put L equals to pi in this discussion, so it becomes way easier, right? If we put L equals to pi, then the pi's cancel with the L and becomes easier to write. But I'm going to stick with it. Since I've made my bet, I'm going to lie in it here. So if we just multiply both sides, right, by, say, f of x times the sine of, let us say, p pi x over L, all right? And what we're going to do is we're going to integrate that from 0 to L. That would be equal to the integral from 0 to L of, and if you don't mind, I'm going to skip a step here. I'm going to go ahead and pass the product inside the summation. B sub n. Oh man, I said I was going to do it, but I didn't. Fine, I'll just leave. I'll do one more step here. I wrote it, so I might as well write it. All right. So this, pulling the summation out, and pull the Bn out, we've got the integral from 0 to L, sine of n pi x over L, sine of p pi x over L dx. How do you integrate a product of sines? This would be a smart formula to have on your formula sheet for the next test, right?